a crazy new way of creating neural network optimizers. What if we, instead of having just one optimizer for the whole model, large language model, different parts of the large language model, feed-forward network, attention heads, embedding layers, they actually are learning different things, and so they should have their own custom optimizers. And I believe that this is actually a very good idea, and this could perform a lot better. This is what one of the creators of the newest, most popular Muon optimizer talked about. You know that we have a weight matrix in a neural network layer. And each row of that weight matrix is a set of weights for a single neuron. So when you multiply input vector with this row, you're gonna give output for a single neuron. And then input vector with the next row, output of the next neuron. So each row is a set of weights for a single neuron. And it turns out that that neural networks learn better if that weight matrix is orthonormal. What that means is, first of all, when you have a vector like input vector and you multiply it with a matrix, the result is gonna be that same vector but rotated and or stretched or squished. So rotated, stretched, and squished. But we want to make a matrix such that the the stretching or squishing doesn't happen, so it's 1. So it's just 1 times that vector when it comes to stretching or squishing, so it doesn't actually stretch or squish, it just rotates. And that way, if our weight matrices are like that, if they are orthogonal, then a neural network will learn faster with less data. So that's how Muon optimizer works. But in this new work, we have even more idea expanding on top of that. First, let's understand on this simple example the idea, the shape of a manifold optimizer. Let's imagine we take some vectors in neural network. That could be just a vector of weights for a single neuron, so weights of a single neuron, or it can be embedding vector of some token or something. And that is what we are optimizing, what we are changing with backpropagation to make the neural network learn, that vector. Now, imagine at the center of this sphere is the 0, 0, 0 coordinates. And we want to make all of those vectors 1 unit long. So when we draw all of those vectors, they go until the surface of this sphere. So if some vectors are, for example, longer, we want to squish them back. So this simple example is actually not explaining that, it's just explaining what this manifold surface is. So in this case, let's imagine a sphere and draw, center of the sphere and draw vectors such that they form a sphere and they're all unit length, equal length. And this is a 3D sphere, but it would work with any amount of dimensions, any amount of vector length, vector dimensions. So this is, you can find the length of a vector by using Euclidean norm, which is basically similar to Pythagoras theorem, but instead of just having 2 of these, you can have any amount. So if a vector has 5 dimensions, 5 numbers, 5 long, then you would just square each of those 5 and add them up just like this formula. And then find the root of all of the entire result. And that's and that should be 1. Or it should be equal, but we want to keep the weights, and the idea here is to keep it at 1. Join my school to become AI researcher, link below. Jeremy says we don't need a difficult or too formal definition of manifold, so he says it's just a curved surface that looks flat when you zoom in close enough. And so if we pick some dot and we zoom in very far, then just immediate surface around that dot would be, let's say, approximately flat. So this is later used for derivatives and gradients, but you can see here, so this plane, red plane, is like tangent space or tangent plane. And you can imagine this plane as showing the valid directions to move to stay on the surface. Now, as I said, it's through just a bit around, very close to this center. So this part of the plane here is way off of surface. But you can imagine this tangential plane here as valid directions to move to stay on top of the surface of the hypersphere. So as we are updating neural network and making it learn, we always want to keep these vectors, which would be single neuron weight vector. For each of the vector is a single neuron, or single vector embedding for tokens. We always want to keep them unit length 1. So one way to do that is to just do the step, optimization step, and wherever it lands, we just project it back onto this sphere, which means we just squish this part back of the weights of the neural weights. That's one way. But we don't want to actually project it or do it like anywhere here. It's better to keep the updates on this tangential plane, because then we can equate learning rate with our step size, which means learning rate is just the length of our step. So if we are projecting anywhere and then projecting it back, then our step size will not necessarily be equal to the length of our vector. Because when we project here, if the vector goes up or a bit or this way, then our actual step is kind of random. It's not correlated with the length of this vector. But we want to correlate it with the length of this vector. So that's why we want to just project it on this plane. So our projection back to the sphere will be correlated with the vector, with the length of the vector, which is our learning rate from center of this. Here Jeremy explains that reason. We are interested in designing methods that take steps in the tangent space, so we can equate the learning rate, which is just our hyperparameter that we decide, like some number, of the optimizer with the actual length of the optimization step. The way I understand in other methods, learning rate is not correlated with length of optimization step, because learning rate is gradient times, the step is gradient times learning rate, and gradient can be any kind of number. So, but here we want to actually correlate learning rate with the length of the step. And even measuring distance in the tangent space, how much in the tangent space we want to move, Jeremy proposes that we do that differently depending on which part of the neural network we are talking about, or the large language model. And when I say gradient, I mean the partial derivative of the loss function, the error our neural network makes with respect to weights. So how do we change weights to improve our loss, or let's say to decrease the error or to decrease the loss? In this example, we're not using L2 Euclidean norm or distance, we're using L1 Manhattan norm. And it looks like a diamond going from 1, 0, 0, 1, minus 1, 0, minus 0, 0, minus 1. L1 distance is a bit weird. So the first time I read it, it says that distance to these corners is equal as the distance to these sides, which is both of them are distance 1. Which is weird because distance to this corner seems larger than distance to this side. But the way L1 Manhattan distance is measured is different. We can just move along these lines or squares or sides of these squares. So we presume that distance of 1 is 4 of these squares. 1, 2, 3, 4. So if we want to get here, it's 1, 2, 3, 4. It's also 1. Here, 1, 2, 3, 4 to get, so any point here is distance 4, L1 distance 4. The idea here is that this pink arrow is the gradient in which direction we should move to reduce the loss, to make our neural network better. And this doesn't have to be on this tangent space or plane. It can be anywhere, in any direction. And so we want to decide where we will actually move based on this gradient. We will move on this plane. As I said, we need to move on this plane. And depending on how we measure distance, L1 or L2, we're gonna use different methods of deciding where to move. So in this case, because we are using L1 distance, we're gonna move in the same direction as the gradient, but we wanna move at the place where we can make like furthest step. And I'm not sure exactly why. Why can't we just move like here, maybe like just parallelly on the plane to this pink vector? I don't know if that's even like known or discovered or explained in this article. Maybe it is. I just didn't understand. Like, why can't we just move parallelly to this vector? Why does neural network learn better if we move in the same direction but the maximum distance we can? But overall, this is just an example how, depending on what type of measuring L1 or L2 or other we do for the distance, we're gonna use different methods of moving on the plane. And this pink arrow doesn't have to be on the plane, it can be anywhere. But this green is on the plane by design, we made it on the plane. And that's our real movement that we will do. So finally, we have a bunch of math, but we will skip that for now. We have this vector going from 0 to this dot, so this is our vector. And that vector on the surface of the sphere has its kinda tangential plane that I was explaining. So we wanna rotate that vector, which could be like a set of weights for a neuron. We wanna rotate it somewhere on this sphere so that it minimizes loss or error of our network. So we want to change the weights that define this vector. And we will do that, you see. So first we will move it on this plane, tangent plane, and then we will project it back onto this sphere. So now the weights of this neuron will have this kind of length and have this kind of setup. So that's how we do it. Move it on the plane to minimize loss and then project back onto the sphere. And finally, this last part, the retraction map that moves it from the plane onto the sphere, is solved with just Pythagoras theorem. After all of this complex math, we got third grade math here. This is the full formula for this update on starting with weights, gradients, learning rate, and then calculating the new set of weights or the new vector. I think it's not too difficult, especially if you copy paste this into ChatGPT or Gemini. Gemini is best, and it can explain this. Maybe we will do this in one of the next videos, dive deeper into this math. To summarize, find the tangent vector on the tangent plane of unit length that goes furthest in the gradient direction. So it doesn't have to be parallel, it can go, if this goes a bit further than this guy. Multiply this direction by the learning rate and subtract from the weights. Or you can say add, depending on how you look at it. So this is our weight vector, this is our movement vector. So if you add them, you're gonna get this vector. I think the reason he said subtract is because our gradient vector will point to the steepest ascent. So we need to subtract the gradient to point to the steepest descent. Nevertheless, in the second step, you will get this long vector, but then we need to go from the plane to the surface. So the third step is retract the updated weights back to the manifold, because the second step gives us weight vector all the way to the surface. We need to bring it back to manifold. And Jeremy says subtract because here in the formula we are subtracting this movement from the weights. And when I saw here as an exercise for the reader, I remember this meme. So proof by contradiction. Proof is left as an exercise to the reader, but there is one more level. The proof is by magic. So maybe next time we will get this forbidden technique only a few know about used in the article. So we're gonna need two things to design our optimizer. It's gonna be our manifold that we constrain the weights to, and it's gonna be the the measuring of the distance, how we measure the distance. And both of those will depend on the role that the weight matrix plays inside the neural network or the large language model, for example. Manifold Muon. This will be easier and faster to understand as we explained everything here already. Typical weight matrix in a transformer or neural network is a vector multiplier. So we have input vector x, weight matrix, and in here in weight matrix, as I said, each of the rows are weights for a single neuron. So input times first row gives you the neuron. Input times second row gives you next neuron, etc. So this is the weight matrix. And usually we would get input x or multiplied matrix multiplied with the weight matrix to get the output y. And as I said before, when you have a vector, starting from here, vector, multiply it with a matrix, it will rotate the vector or stretch or squish the vector. And you can watch about this in 3 blue, 1 brown. And for neural network to learn faster, we want this weight matrix to just rotate the vector. We don't want it to stretch or squish. So there are two reasons as I understand. The first reason is because we are doing a lot of these multiplications. If everyone squished this vector a little bit, then this vector would be very small and we will have a number of problems with that. Not just a number underflow that cannot be represented in GPUs, but other problems. Or it could be like very big. So, but if we just rotate the vector, then it's not going to be stretching or squishing. So imagine that x is our vector. When we multiply it with the matrix W, we will get our y, which is the rotated version of the x, and we don't want y to be stretched or squished. We want it to be same length. And the second reason to keep these W matrices just rotational is because neural network learns faster with less data if we do. This is how Muon optimizer works. So Muon is the predecessor of this Manifold Muon. And I'm not sure why, and I'm not sure if we even know, if anybody knows why it learns faster with less data. I have on X, this guy Su Jianlin is inventor of ROPE, rotary positional embeddings, but he talks about Muon optimizer in his blogs a lot. It's in Chinese, but you can use Gemini or Kimi to translate it. I think it's very good. I think he understands it as good as these other people who are inventing it. And he invented ROPE when he was 2 years older than I am right now. And ROPE is used by every company, AI company in the world, so my time is running out. In order for a matrix not to stretch or squish vectors, its singular values need to be 1, exactly 1. And there is this Stiefel manifold. It's a surface, and if a matrix is on that surface, its singular values are 1, and it's not stretching or squishing vectors. And you can define these matrices as a matrix when multiplied with its transpose gives identity matrix. So this is identity matrix. It has ones on the diagonal and zeros around, and when you multiply any vector or matrix with this matrix, it will not change at all. It will stay the same vector or that matrix. It is a little bit confusing to me. How can a matrix be on a surface? As I understand, like a dot or a vector is on a surface, not a matrix. But the way Gemini explained to me is you flatten entire matrix. So if it's 2 by 2 or 3 by 3, you just put it all in a single vector, all of the numbers in a single vector. And then that can define a spot. I hope this is a correct way to visualize it. But regardless, this is the definition. So multiplied with its transpose gives identity matrix. Those are the matrices that have singular value of 1. So in essence, they just do what we just explained the whole video, calculating the gradient, moving it on the tangent, and then retracting back. And quite surprisingly, they have also code implementation. And I'm probably gonna use this for my thesis because I didn't mention that I'm gonna do this for my thesis, something like this probably, maybe even like exactly continuing from this research. And so this code is very interesting. This is hyperspherical descent. We're flattening weights, flattening gradients. In the next part, we calculate the update tangential to the sphere on the tangent plane. In the next line of code, we will normalize to make this direction vector, tangential direction vector on tangential plane have unit length. And this small number is just to avoid division with 0. And then this eta is the learning rate. So we will multiply our unit vector with the learning rate to get a vector that has the direction as our direction vector, but has magnitude or length of the learning rate, which is a lot smaller, which is like 0.001 or something. And we subtract that from weights because, as I said, gradients will show the direction of the steepest ascent of the error of the loss function. So we want to change weights so that our gradient goes in the opposite of the gradient. I mean, our update goes in the opposite direction. And so remember that now, because we moved on the tangential plane, now this spot may not be on our sphere. So we need to bring it back to the surface of the sphere, and this spot is just vector from the center of the sphere to this spot. So if we divide this vector by its norm, we make it unit length 1, then it will just fall back onto the sphere. And now that we are finished, we want to return this back to the shape of a matrix because it was one flattened vector. So my visualization that was explained by Gemini was correct. We turn a matrix into a long flattened vector of just one array of numbers, and that's how we can imagine it as dots on a surface or off the surface of a sphere. This code is a bit confusing, or I'll just take a look into this in one of the next videos or another time, and then I'll explain it as well. Here they show a small experiment where the red line, Manifold Muon, achieves higher test accuracy and train accuracy than the AdamW optimizer. This needs to be investigated even more. Make sure that all of them are properly tuned, properly designed. But interestingly, singular values here for Manifold Muon, they stay at 1, while for AdamW it's different. Actually, Sujian Lin got mentioned so many times here, I didn't even notice. And there is a lot of further reading here, which is interesting. I'm gonna take a look into this as well. And lastly, in Modular Manifolds section, it says that up until now we were talking just about a single layer in a neural network or LLM, but they usually have many layers, like many layers of transformers, or even different like heads of attention mechanism or feed forward, or within the feed forward there are multiple layers. So the main problem here is how do we decide learning rates for each of these layers? So they should probably be different learning rates for each of the layers. Right now, we use a single learning rate for the entire model, but this proposes we use different learning rates depending on what layer we are optimizing. And we don't want to do it by hand, by trial and error. This is inefficient and not good. We need to have some way of determining learning rates. And this part explains how to calculate the learning rate and how to stitch these layers or blocks together. This can be even entire blocks in the neural networks, not just individual layers. But guys, I think I'm gonna end the video here, and I might dive into all of this deeper in one of the following videos, mainly because I've been trying to record this video for the past 3 hours. I started 9:31, now it's 12:37. So 3 hours of this heavy thinking. I was trying to understand everything and then explain. But I'm gonna make more videos about this, especially when the videos about my thesis that I'm doing. And there is future work here. Like, what manifolds should attention heads live on? Should embeddings be constrained differently than unembeddings? We can mix and match constraints in different parts of the network or leave some tensors unconstrained. So maybe I'll do my thesis about this or some of these below, I'm not sure yet. Check out other videos on my channel and see you next time, see you soon. Also join my Discord where we do all together AI research, LLM research, etc.